now consider ourselves masters of probabilistic modeling. If there's some random quantity that we have in mind, we can propose a notorious distribution to perhaps model it, or even just create a distribution that has a shape that we really like. So we want to model the number of items that someone has in their cart at checkout. Well, zero truncated Poisson. If we want to model the amount of money that someone spends with a store over the course of a month, well, probably Lognormal, or some function that we want to propose here. But what if we want to add in a bit of extra realism to our models that the models in the notorious zoo, or maybe our own proposals, can't quite capture? So let's consider the following scenario where we're considering a telemarketer. So this telemarketer calls up people, tries to sell a product. Sometimes they succeed, sometimes they fail, sometimes they make a sale, sometimes they don't. And what we'd like to do is to study the number of sales that the telemarketer makes over the course of a day. Now, if we knew the telemarketer made 100 phone calls, we could draw from the notorious zoo to answer this question. We know that the number of successes out of a certain number of trials is binomial, so the number of sales out of 100 could be modeled by a binomial distribution with n equals to 100 and p equal to 20%, whatever the chance is of making a sale on each individual call. But what if the number of calls that the telemarketer makes each day is somewhat random? Maybe it's a little bit more than 100 on a particular day. Maybe it's sometimes a little bit less. Sometimes the telemarketer's in their groove and can call up a lot of people. Other times, maybe calls just take a long time, so the telemarketer doesn't call as many people. So what if we have this second layer of randomness? What if the number of calls the telemarketer makes is considered a random quantity? Maybe a Poisson random variable, our generic count without a context model here. And so how can we incorporate this extra layer of randomness, which really translates into an extra layer of realism? If we knew the number of calls the telemarketer was going to make, binomial. But if that number of calls is random, what do we actually do? So let's actually simulate this process just to anticipate some of the key results. So what we can do is we can generate at random, let's say 100,000 number of calls that the telemarketer is going to make. So consider the number of calls over the course of 100,000 days, and let's imagine that this is coming from a Poisson distribution with an average of 100. So if we make a histogram of the number of calls that might be made, it's probably somewhere between 60 and 140 or so, peaking close to 100. And so let's imagine that the number of calls, is in accordance with this distribution, random from one day to another. Let's say that the telemarketer has a 20% chance of success. And so let's look at the distribution of the number of sales the telemarketer makes. So we can run the R-binom function. We can ask for 100,000 random numbers from this. The size parameter, the n parameter, we're going to use whatever number is stored in the n calls vector. So sometimes 80, sometimes 120, etc., but with a constant probability p of success. So if we generate the number of sales from day to day here, we can get a histogram of the number of sales. And then we can say, well, how does this histogram compare to the case when the number of calls was fixed at 100. So let's also generate 100,000 random numbers from a binomial distribution when n is fixed at 100 and compare these two. Well, what we see is that by injecting an extra layer of randomness, the number of calls being a random quantity, the distribution is a little bit more variable than if the number of calls was fixed. So what we have is that the black histogram is just the plain old binomial, 100 per day. The red histogram is the binomial with a Poisson number of calls. And we can see that the Poisson plus binomial is a little bit thicker. There's a little bit more variation in the number of sales that we can expect to see. And that's very common in the real world. Very often, some of these notorious distributions do fall short because real-world data tends to be a little bit more variable than what the notorious distribution can actually provide. So back to comparing just the vanilla binomial with the Poisson number of trials, we can see that in this case we have the same average of 20 sales per day, but adding the extra layer of randomness on that number of calls increases the standard deviation of the number of sales up to about 4.5 versus about 4 with that vanilla binomial. And so this is something that we exploited actually back when we were discussing the discrete notorious zoo. We talked about how the negative binomial, which nominally counts up the number of failures until the rth success, was actually a good backup for the Poisson distribution if the Poisson distribution just wasn't quite cutting it, if there was more variability in the data. So let's compare those two histograms just to see. Well, if we generate x and y to be Poisson random numbers and negative binomial random numbers, we can have the same average for both of those distributions, but the standard deviations of the two can differ. For the negative binomial, a little bit larger. So same average, standard deviation for the negative binomial a bit larger. Comparing those histograms, we can see a very similar effect here, like when we added the Poisson randomness to the number of calls the telemarketer was making. That negative binomial in this case is just a little bit wider, a little bit more variable than what the Poisson distribution is, and very often that's just the right recipe for what we need to do modeling in the real world. A lot of these notorious distributions don't offer us quite enough variation in values to be reflective of what we end up capturing in real-world data. So let's work on this. Let's try to develop a framework that allows us to inject an extra layer of realism by actually treating the parameters of these notorious distributions, the n or the p of a binomial, the mu or a sigma of a normal distribution, as random quantities themselves. When we do this, we get to add a little bit of extra spice, a little bit of extra variation into the possible values, and sometimes that's exactly what we need. So for the telemarketer example, here's how I'd like to represent the probability model. We know that given the number of calls on a particular day, we'll call that capital N, the distribution of the number of sales is going to be described by a binomial distribution with capital N trials and a probability of success of P. That little twiddle is just probability shorthand for how's the probability distribution of. And in this case, what we want to do is actually ascribe a probability model to that capital N parameter, the number of trials. So we're going to say N twiddle Poisson with a parameter lambda, an average value of lambda. And so this is what we refer to as a hierarchical model, because there's a hierarchy of random parameters. Given the value for the number of trials, we know the number of sales is binomial, but the number of trials is random, in this case given to us by a Poisson. So we have a top layer and a bottom layer, and what can we do with this? Well, along with that telemarketer example, maybe the number of calls is fixed. Maybe the policy is, hey, you got to stay and make calls until you've made 100 of them. What if the probability of success varied from one telemarketer to another? So maybe some telemarketers are very skilled. Their chance of making a sale more like 25%. Maybe other telemarketers not so great. Maybe the chance of their sale is 10%. Maybe x given capital P, the probability of success, is a binomial distribution with n of 100 and that probability P, but P has a probability distribution ascribed to it. P goes between 0 and 1, so maybe the beta distribution would provide an extra layer of realism to describing the variation in probability of success from one telemarketer to another. Or it might be the case that we're studying the failure times of light bulbs. And with a very particular recipe, the distribution that describes the failure time for light bulbs might be well described by an exponential distribution with a parameter lambda, a rate of failure. But we can imagine that each day these light bulbs are being manufactured. The people that are working the line, the recipe might be a little bit different. The manufacturing process might be a little bit different as well. It very well may be the case that lambda, that rate of failure associated with the exponential distribution, is actually a bit random itself. Maybe some days it's 12.3, other days it's 9.5. We could add that extra layer of realism, capturing the fact that that lambda parameter isn't really a fixed quantity. It might vary from day to day by looking at the process in terms of a hierarchical model. So x given lambda is exponential, but lambda has a distribution on its own. Maybe it's uniform between two values. Maybe it has a different notorious distribution here. And this very often would come up when studying customer segments. It very well might be the case that given what customer segment that we're dealing with, the distribution of the amount of money that people spend is well modeled by a normal distribution or a log normal distribution. But maybe those parameters, the mu and sigma, depends on what segment we're talking about. Maybe we have big spenders, medium spenders, low spenders, with different probabilities of finding each. So we'd have the top level of the hierarchy saying x given the segment, essentially the mu and sigma parameter, might be a log normal, but there's a probability distribution on the segment itself, the combination of mu and sigma parameters, associated with high, medium, and low here. So very often this is what we'd like to do. We'd like to extend a model we have in the notorious zoo to add an extra layer of realism by treating some of the parameters of those notorious distributions as random quantities themselves. And so the hierarchical model framework provides us a way to do this. Now, in general, this is the way that the notation works. What we're going to do is have the top layer of the hierarchy give the conditional distribution of our random variable x, what we're studying, the number of sales, for instance, given a particular value of the parameter of the probability distribution we're using to model it. So given theta, which is going to be our generic placeholder for some parameter that the distribution depends on, x given theta has a known distribution, so the conditional distribution of x, given that we know we're given a particular value of theta, is a Poisson, it's a binomial, it's an exponential, it's a normal, etc. But that parameter, theta here, is going to have a probability model of its own, so the second layer of that hierarchy. So that's our notation. Let's try to work through a few examples just so you can see how this works and how useful this really is. So in our telemarketer hierarchy, we have the following conditional distribution. X given n, the number of calls for the day, is binomial, but that number of calls each day is random, and it's going to be described by a Poisson distribution. So how could we get the distribution of the number of sales just all by itself? How can we free it from the dependence on the random number of calls each day? In other words, how do we get the marginal distribution of x? So in the hierarchical model, we have a conditional distribution of x for a particular value of that random parameter. We want to free ourselves from that random parameter by taking into account its probability distribution to get the overall kind of standalone distribution of x, which we refer to as the marginal distribution. Well, we're going to borrow a page back from our study of conditional probability and actually do the partitioning trick. So you might remember an example back when we studied conditional probability of trying to figure out the probability that you would win against the next opponent that you played on a video game. But the problem is that there were three different types of opponents. There was a hard, an average, and an easy. And each of those opponents had a different probability of winning against. So how did we do this? Well, we pieced together the probability of winning, the marginal probability of winning, by partitioning over the possibilities for the opponent that we might face. So for each possible opponent that we might face, the hard, the average, the easy, we multiplied the conditional probability of winning against that particular type of opponent times the probability of facing that opponent. After methodically going through all possibilities for the type of opponent that we might run into, we were able to sum up the values and come up with that marginal probability, just the overall probability of winning. And so we're going to take a similar approach here. If we do want to have the marginal distribution of the number of sales, well, we're going to partition over the number of calls. Just like we partitioned over the opponent that we faced, the average, hard, easy, we're going to consider values of calls of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, etc., all the way up to infinity, because the Poisson distribution allows any value of x that's bigger than or equal to 0. And we'll see how those probabilities add up. And in general, that's really what we're going to do. If we're interested in the marginal distribution of our random variable, capital X here, what we're going to do is this partitioning trick. We're basically going to partition over all the possible values of that random parameter that dictates the conditional distribution of x. And once we've done that partitioning, once we've done the appropriate mathematical procedure, we'll have freed the dependence of x on the random parameter there, and we'll get that marginal distribution emerging. So let's go ahead and do this for the telemarketer example here. So to partition, to get the marginal distribution of having capital X, the number of sales made, equal to little x, a very particular value, we'll just loop through all the possible values for capital N. So what is the probability of getting little x sales given big N is equal to 0 times the probability that big N is equal to 0? plus the probability of having little x sales given big N was equal to 1 call, times the probability of having 1 call. Just like we're looping over the difficulty of the opponents, we're looping over the possible values for the number of calls that were made that day. Now, in this case, if I have a particular value of little x in mind, obviously I need to have at least that many calls being made. So I'm not going to partition from values of capital N of 0 up to infinity. I'm going to start out at a capital N equal to x. Corresponding to a 100% success rate, I have to have made at least little x calls to have little x sales. So if I were to write this in summation notation, I'd be taking the sum of little n equal to x, starting at x, going to x plus 1, x plus 2, all the way up to infinity, of my conditional distribution for the number of sales given that number of calls, which is that binomial distribution, times the probability of getting that number of calls, which was a Poisson distribution. Both of those PMFs I can look up, I can write down. I have a pretty complex looking sum, can't lie, that's rather intimidating. But wouldn't you know it, Wolfram alpha is a champ. If you throw that equation into Wolfram alpha quickly spits back that, okay, this sum actually has a pretty simple value, and it looks like lambda p to the x, e to the minus lambda p over x factorial. Well, if you look at this and you say, hey, I've seen this before, I kind of recognize this, this formula, well, great memory, because this actually is the PMF of Poisson distribution. Just instead of having the parameter lambda, it has the parameter lambda times p. So we've made a rather interesting discovery here. So if for a particular number of calls, the number of successes is well described by a binomial distribution, but if the number of calls is random and the number has a Poisson distribution itself, it turns out that the marginal distribution of the number of sales, after you disentangle its dependence on that random number of calls, turns out to also be a Poisson distribution with parameter lambda times p. And that kind of makes sense. We know the parameter of a Poisson distribution is the average of that distribution. Lambda is the average number of calls made. P is that probability of success of each individual call. Lambda times p is the average number of successes. So that kind of has that nice logical matchup that looks pretty good. And so whenever we're faced with this hierarchical model framework and we need to figure out what the marginal distribution of capital X is, our random variable of interest, we need to free ourselves from the random nature of that parameter that the distribution depends on, we're going to do that partitioning trick. So one more example. Let's imagine that we have two customer segments. We have some big spenders and we have some small spenders. So there's a 25% chance that the person that, say, walks into the store next is going to be a big spender, and there's a 75% chance that the next person walking into the store is going to be a small spender. Now, the good news is that the probability distributions of the amount of money that both of these groups spend is well described by a normal distribution with a standard deviation of 75. It's just that the big spenders and the small spenders have different averages, different values of mu. So in this case, if we're dealing with a big spender, mu is going to be equal to 500. If we're dealing with a small spender, mu is going to be equal to 200. So I can write this scenario as a hierarchical model. Basically, x given m, let's say our abbreviation for what the average of the distribution that we're worrying about. X given m is a normal distribution with a mean of m and a standard deviation of sigma, 75 in this case. But m is going to be a random variable. It has a 25% chance of equaling 500 and a 75% chance of equaling 200. So how can I get the marginal distribution of the amount of money that this customer is going to spend? The next person walking in the door might be a big spender, might be a small spender. Well, I can partition over the type of customer this person is. So just like that last example where we partitioned over the possible values for capital N, the number of calls, from little x up to infinity, we're just going to partition over the possible values of mu that we might end up seeing. There's only two possible values here, so it's actually relatively straightforward. And so we'll write out that marginal distribution, our little f of x, that normal distribution, as the sum of the conditional distribution given a particular value of m times the probability of observing that value of m, summed over all the possible values of m in our model. Only two in this case. And so in this case, well, I can write that out, and what it looks like is I have a weighted sum of two normal distributions. A weight of 0.25 assigned to the big spenders, 25% chance of seeing them, with a mean of 500, and a 75% chance of seeing a small spender, mean of 200, so the weight given to that normal distribution is like a 0.75. So I've recovered a fairly complex formula for my PDF, but here's going to be the remarkable thing. If I make a plot of that PDF, I find a bimodal distribution. And this was something that no distribution in the notorious zoo could produce alone. If we ever made a histogram of our data values and we saw bimodality, we immediately frowned a little bit because there's no distribution in the notorious zoo that allows for bimodality. And so here's a way in. You can actually get a bimodal, trimodal, as many modes as you really want, distribution within this hierarchical model framework with very little effort. You basically say, well, let's kind of mix together a bunch of different normal distributions, a bunch of different log normal distributions. There's a 75% chance of seeing this normal, a 25% chance of seeing this normal. We can write that in that hierarchical model framework, and out will come bimodal, multimodal distributions. So kind of a fantastic way to approach really difficult looking distributions. See some bimodality? Well, maybe try one of these hierarchical models. And so this is why hierarchical models actually have another term associated with it called mixture models, because sometimes you're just kind of mixing together different distributions. This one normal distribution with another distribution, depending on what segments of the customer that we're looking at. So in general, if we have a hierarchical model and we want that marginal distribution of our random variable capital X, freeing it from the dependence on the random parameter that dictates the conditional distribution, we're going to do that partitioning trick. If the possible values of the random parameter is a discrete distribution, it works out as we've described here. But what if the possible values of that parameter is actually continuous? So what if, that manufacturing process that's making those light bulbs, we have a time to failure that's well described by an exponential distribution with a parameter lambda, but maybe lambda is any value between 3 and 100. So how do we take into account when the distribution describing our random parameter is continuous? Well, instead of doing a sum over all the possible values of that random parameter, we're going to replace the sum with just an integral. Much like what we did when moving from discrete world to continuous world for probability distributions, whenever we go from discrete to continuous, we're always replacing sums with integrals. But it's the same overall idea. So if I want the marginal distribution of capital X, the probability distribution of X all by itself, disentangled from that random parameter, I'm going to go through and essentially partition over all the possible values of that random parameter. But instead of summing over all the possible values, I'm going to integrate over all those possible values instead because I have a continuum of possible values. So let's see how this works. Let's imagine the following hierarchy. So let's imagine that we're working for Coke, or we're working for Pepsi, or maybe RC Cola, and we're interested in modeling the amount of soda that's actually going into the soda cans. Now, by design, the label actually says that there's 355 milliliters, but we know better there's going to be a little bit of randomness due to the manufacturing process, so sometimes there's a little bit more, and sometimes there's a little bit less. So maybe overall, given a particular way of filling up these cans, the amount of beverage inside the can might be well described by a normal distribution with a mean of 355 and maybe a standard deviation of 6. But what if there are manufacturing variations? What if on average it's not always 355, but sometimes it's a little bit more, sometimes it's a little bit less, depending on who's working, the specific procedure that's being used to fill up those cans? What if we have the following hierarchy, where the mean of that normal distribution is a random quantity? So our hierarchy would look like this. X given capital M, kind of our placeholder for the random mean of that normal distribution. Conditional distribution X given M is normal with a mean of M and a standard deviation of 6, but M itself is a random quantity, and let's say that a probability model for M, the average value for that day, is also a normal distribution with a value of 355 for the average and a standard deviation of 0.5 from day to day here. So there's our hierarchy. what's the probability distribution of the amount of soda that goes into a can in general? How can we free ourselves of the dependence of that distribution on the random parameter that's describing the average of that normal distribution? Well, we're going to partition over all possible values of what that average might be. Instead of summing over all the possible values for what m might be, we'll take the integral because it's a continuous quantity, and so we can write out our equations. The marginal distribution of the amount of soda is going to be the integral of our formula for the conditional distribution of that amount given a particular value of m times the probability distribution of m itself. We'll integrate over all the possible values of m. This looks pretty hairy, but if we ask Wolfram Alpha nicely, hey, can you do us a favor, calculate this integral for us? Wolfram Alpha comes back and says, sure, friend, I got you. And here's our formula for the marginal distribution of the amount of soda. And looking at that formula, we recognize it. That's actually the formula of a normal distribution. And in fact, we can immediately identify what the average and the standard deviation is of that normal distribution. It has an average of 355, the overall average that we were kind of expecting, and with the standard deviation that's actually kind of a mixture of the two standard deviations that were involved in the hierarchy. The standard deviation of 6 that describes the variation on a particular day once that mean has been chosen, and then also the sigma, the standard deviation of how much the mean varies from day to day. So specifically, how does that work? Well, there's the very general following result, that if we do have the following hierarchy, where the conditional distribution of x given the mean is normal with a mean of m and a standard deviation of sigma 1, and that mean m is a random number from a normal distribution which has a mean of mu and a standard deviation of sigma 2, we can immediately write down that the marginal distribution of x is also a normal with a mean of mu and a standard deviation that kind of is found from the Pythagorean theorem. Squaring up the two standard deviations involved and then taking the square root of the result. Kind of like the hypotenuse is the square root of the sum of squares of the other two sides of the triangle. All right, and then one last example, back to the telemarketer example. What if every telemarketer has to make a specific number of calls n? They can't leave until they do. And in this case, we inject the extra realism by saying, well, not all telemarketers are created the same. Some have higher values of p, some have lower values of p. P is going to be a random variable that differs from, say, person to person. So we could have the following hierarchy. X given p, our conditional distribution of the number of sales given a particular value of p, is a binomial distribution with parameter n, that fixed number for the number of calls, and p. But p is going to be random. P goes between 0 and 1, so the beta distribution, the natural domain for values that are constrained to live between 0 and 1, might be a good probability model that describes the possible values of p we might see. What could we come up with for the marginal distribution of x, the number of sales in a particular day? How can we free ourselves of its dependence on the probability of success, which is going to be random? All right, well, we have to get into a little bit of notation. So the beta distribution, if we go and look at the formula for the PDF, it has this crazy symbol, this capital gamma, which is really just the generalization of a factorial function. Essentially, gamma of n plus 1 is just n factorial. But the gamma function, you can plug in decimal amounts to it, you'll get a number back. Factorials only work for integers. The gamma function works for integers and everything in between. And so you ready for this? Here's what the marginal distribution looks like. So how can we get the marginal distribution of the number of sales? Well, we can go through that same procedure. We can take into account all the possible values of p we might see and to kind of weight those distributions together to get the right answer. So the way that we do this is essentially partitioning over all the possible values of p, but instead of taking the sum, we take the integral because p is a continuous quantity. So as we do this partitioning, what we do is we take our formula for the conditional distribution of the number of sales given p. That's our binomial distribution. Notice that I've rewritten the factorials like n factorial as gamma n plus 1, x factorial as gamma of x plus 1, just to keep the notation kind of consistent here. So there's my conditional distribution of x given p, and then I multiply that by my distribution of p itself, my formula for the beta distribution. Looks really hairy, but I want to integrate that expression from 0 to 1, integrate over all possible values of p, And when I do that, I actually come out with an equation that is doable. I can program that into R actually without too much difficulty, but it just involves a whole bunch of gamma functions. And so this would be the probability model for the number of sales that telemarketers would make when they all have to make exactly n calls on a particular day, but the probability of success from telemarketer to telemarketer is described by a random quantity by some beta distribution. So this distribution actually has a name. It's kind of a sideshow attraction in the notorious zoo. It's called the Beta-Binomial distribution. You'd have to install a package in R to actually use it. But once you have that package, the functions, the D, the P, the Q, the R functions work as everything else. So we could generate, say, random numbers from this Beta-Binomial distribution and just look to see the results here. So in this case, we're saying we have a fixed number of calls of 100, and the distribution that's describing the probability of success is a beta distribution with parameters 2 and 5. So if that's the case, well, let's just generate a whole bunch of random numbers for the number of sales that are made, and we get the following histogram. So a lot wider than what a classic binomial distribution would actually give us. We're able to inject that extra bit of realism that might be necessary to fully describe the situation. Now, one last thing before we move on, remember we were talking about how that negative binomial serves as a really good alternative to the Poisson when there's just more variation in the data, a larger spread of values, than what the Poisson distribution can actually provide us. Well, the reason why the negative binomial distribution works so well is that we can actually derive its formula in the context of a hierarchical model. We introduce the negative binomial distribution as the number of failures that occur before a set number of successes, but we can actually derive the formula for the negative binomial in a completely different context, which explains why it's a good backup for the Poisson. So consider the following hierarchical model. Let's imagine that we're counting up something, so capital X is our count of something, and we like the Poisson distribution, and so for a particular value of, say, lambda, x given lambda is a Poisson distribution, but the lambda parameter of that Poisson is random. It has a bit of variation. So let's imagine that in the second layer of our hierarchy, we say that the distribution ascribed to lambda is a gamma distribution. And let's write the two parameters as follows. It turns out that if you go through the math and ask, okay, well, what's the marginal distribution of capital X here? What is the distribution of this count free from the randomness associated with that lambda parameter that describes that Poisson? When you go through the math, you find out that the distribution of X turns out to be a negative binomial distribution, and so there we have it. That's why that negative binomial is a great alternative to the Poisson. It's basically describing the case where your count should be Poisson, but that lambda parameter has a little bit of extra randomness associated with it. So we get a little bit of a larger spread of values. As we've seen, getting the PMF or PDF of the marginal distribution of X, kind of freeing ourselves from the random nature of the parameter that the conditional distribution depends on, can be really a lot of work. And very often we don't want to know what the probability distribution is in its entirety. We just might be interested in knowing what the average value is and the standard deviation when we choose to model something in a hierarchy. And so there are some shortcuts where we don't actually have to derive the full probability distribution for X in order to get these quantities. There are two laws, the law of total expectation and the law of total variance, that will allow us to at least get the expected value and the variance, which in turn gives us the average value, the expected value, and the standard deviation, that square root of the variance. Now, the notation for this looks a little bit hairy, so bear with me. It turns out that actually working through this typically isn't so bad. So our generic terminology for when we model something with a hierarchy is as follows. We say that theta is our placeholder for that parameter that's controlling the shape of the distribution. So it's the lambda parameter of the Poisson, the mu, the sigma of the normal distribution. The conditional distribution of X given a particular value of theta here has a known formula, the formula for the Poisson, the formula for the normal, but that parameter is random in itself. There's a PDF or a PMF that describes its possible values. So X given theta, twiddle f, some conditional distribution that we know, but theta, twiddle the distribution given to theta itself, a different distribution that we use in our model. So once we write our hierarchy in that form, here's how we can very quickly get the expected value of x. Kind of taking into account the random nature of theta here, what we do is we employ the law of total expectation, which asks us to calculate two expected values. So step number one, what we're going to do is we're going to pretend that theta is some fixed quantity, and we're going to get the expected value of x in terms of theta here. So we know the expected value of Poisson is just lambda. The expected value of the beta distribution is alpha over alpha plus beta. And so if indeed those parameters were really random and we're using them in a hierarchical model, we'll start out step one just by writing down the expected value of x in terms of what those parameters are, just assuming they're fixed for right now. Now, when we do that, we get a function in those parameters. Expected value of the beta is alpha over alpha plus beta. The expected value of a binomial is n times p. Step two is going to say, okay, well now, with respect to the probability distribution of that parameter, let's get the expected value of that function. Once we do that, by the law of total expectation, that is going to be the expected value of our random variable x. So we've really got to work through an example in order to really understand this. And so let's go ahead and work through the Telemarketer example. The only two things that we really want to be aware of, that we want to remind ourselves about how expected values work, is the following. Number one, if I ask for the expected value of a times x, where a is a constant, I'm scaling it up by maybe 2, dividing it by 5. The expected value of a times x is just a times the expected value of x. And then also if I'm taking the expected value of the sum of two different things, like x plus x squared, I can write that as the expected value of x plus the expected value of x squared. The expected value of a sum is the sum of the expected values. So let's dive right in. In our Telemarketer example, our hierarchy was that the conditional distribution of x given n, the number of sales given a particular number of calls, was a binomial distribution with parameters n and p. But n was random, n had a Poisson distribution with a parameter lambda, an average of 100 for instance. So how can I get the expected value of the number of sales, the expected value of x? Okay, well, step one says, well, pretend that n is just a fixed number and get what the expected value is in terms of n. So if I go and look up, what about the binomial distribution? What's the average value, etc.? I find that the average value of the binomial is just n times p, the number of trials times the probability of success. So step one is to just figure out what the formula is for the expected value of x in terms of that unknown parameter. So we get a function, capital N times p, and now we say, okay, now let's take into account the random nature of n. What's the expected value of that function? All right, well, in this case, the expected value of capital N times p. P is just a number. I can pull that out in front of the expectation. So the expected value of n times p is just p times the expected value of n. Well, n had a Poisson distribution with parameter lambda. The expected value of Poisson is its parameter, lambda here. So the expected value of n is just going to be lambda. Therefore, I have found the expected value of x by itself with the law of total expectation. The expected value for the number of sales is just p times lambda. All right, another example. Let's imagine that the amount of money that people spend at a store is well described by a Lognormal distribution with parameters m and sigma. Sigma we're going to keep fixed at some value, but m might be a random quantity in itself based on what customer we're looking at. Some customers spend, a lot because they're rich. Some customers spend a lot because they just want to show off. Some customers might spend not so much, they're a little bit stingy. So m we might be interested in treating as a random quantity. And so we would have the following hierarchy. The conditional distribution of the amount spent given m is a Lognormal distribution with parameters m and sigma, but m is a random quantity. M, let's go ahead and take as having an exponential distribution with parameter lambda. So the distribution of m kind of falls off quickly for larger and larger values of m. M being pretty small is more common than m being large. So I would like to know what is the expected value of the amount of money that people are spending under this hierarchy. If m was a fixed number, I could look that up pretty easily just by going to the Wikipedia page for the log-normal distribution. And the formula for the expected value of a log-normal random variable is just e raised to the mu parameter, which we're representing by capital M, plus sigma squared over 2. And that's what I want to do for step 1 for my law of total expectation. Just pretend for the moment that m is a fixed number, that mu parameter is fixed for the log normal, and go ahead and look up its expected value, or derive it. So once we've done that, we found a function with our random variable m here. And so step 2 says, okay, well now let's take into account the random nature of m. M had an exponential distribution, so what is the expected value of the function e raised to the m plus sigma squared over 2? And so now we got to think back and say, okay, there's actually another property of the expected value I need to remember. How do I, in general, find the expected value of a function, g of x? Well, it's actually not so bad. I just take my formula for g of x, my function of interest, multiply that by the PDF describing the random variable. After I multiply those two things together, I just integrate over the range of possible values. So if I want to know what's the expected value of the function e raised to the m plus sigma squared over 2 power, I take that formula, multiply that by the formula of the PDF of the exponential distribution that's describing the random nature of that m parameter. I throw that into Wolfram Alpha and say, all right, help me out. And Wolfram Alpha says, okay, well, it looks like the answer is e to the sigma squared over 2 times lambda over lambda plus, minus 1. Now, Wolfram Alpha will say, hey, there's a restriction on what lambda can actually be. Lambda has to be bigger than 1, and it makes sense because if I look at the formula for the expected value, if lambda was less than 1, that would give a negative value, and we can't have negative amounts spent. So, I guarantee you that's a lot easier for getting the expected value in this hierarchy than trying to derive the marginal distribution of x and then getting the expected value of x by taking that formula, multiplying by x, and integrating over the whole range. So getting the expected value of x in a hierarchical model isn't so bad. We just have to calculate two expected values, one with respect to the conditional distribution that we're dealing with, and one with respect to the distribution on the random parameter that we've ascribed. Getting the standard deviation is actually substantially more tedious, unfortunately. So just like when we were getting the standard deviation of a random variable, we're actually going to get the variance of the random variable first, and then we're going to take the square root. So here's what the law of total variance has to say about getting the variance of x kind of free from its dependence on that random parameter theta. We have to do a few things. So what we're going to do is get the variance by adding up two separate values. The first value is going to be the expected value of the variance of the conditional distribution of x given theta. The second term is going to ask us to calculate the variance of the expected value of x given theta here. Now that's really a mouthful. We're going to have to work through an example to see how this works, and it's a lot of math. There's really no great way around this one. So back to that telemarketer example, we'll start with an easy one. We have the hierarchical model that given a number of calls, the number of sales is described by a binomial distribution, parameters n and p. But n's a random quantity, the number of calls each day is going to vary. The probability distribution we're going to give to n is Poisson with a parameter lambda. So we've talked about the expected value of x, that's just lambda times p. What about its standard deviation? What's the give or take associated with the probability distribution? All right, so step 1 says go ahead and find the expected value and the variance of x, assuming that n is a fixed number here. So we go and look up the formulas for the binomial distribution, and we find that the variance of a binomial is just n times p times 1 minus p. And the expected value is just n times p. So the law of total variance says, okay, we'll take your formula for that variance. That's a function of your random parameter here. It's a function of n. And let's calculate its expected value. So what's the expected value of n times p times 1 minus p? Well, we're going to use that property once again, that the expected value of a times x, where a is just a number, is equal to a times that expected value. So we're simply going to take out that p times 1 minus p out in front of the expected value operator, and we're going to find very quickly that the expected value of that variance of x, written in terms of n, is just p times 1 minus p times the expected value of n. Expected value of n, Poisson, that's just lambda. Okay, so we also have to go through and say, okay, well, what's going to be the variance of our formula for the expected value of x? The expected value of x is just n times p, so what's the variance of n times p? Well, in this case, I'm going to exploit what are the properties of the variance that I remember, that if I have the variance of, say, a times x, just some number times x, I can take that a in front of the variance, I just have to square it. So the variance of n times p, p being a fixed number, I can take that in front of the variance just by squaring it. And so the variance of n times p is just p squared times the variance of n. I can look up the variance of a Poisson random variable. It's also just lambda. So the variance of n times p is p squared times lambda. Almost there. We do the addition, and we find that the variance is p times lambda. And this is something that we actually already knew because we derived the marginal distribution of x, kind of freeing ourselves from that random dependence on the number of calls. We saw that it was Poisson with a parameter lambda times p, and we know that the mean of a Poisson and the variance of a Poisson are both the parameter itself. So no big surprise here, we just recovered something we already knew. Now for a more in-depth example. So back to that spending example where given a value for m, the mu parameter of the log normal, the distribution of the amount spent is, well, described by a log normal with that mu parameter and sigma. So we're going to take sigma to be a constant, but that mu parameter, capital M, is going to be a random quantity that's going to differ from one person to the next, and we're going to say that that is going to be well described by an exponential distribution with parameter lambda. So let's go ahead and calculate the variance of x here using the law of total variance. So step 1 says, let's go and get the expected value and variance of x, assuming that m was a fixed quantity. So we head over to Wikipedia and we say, okay, here's my formula for the variance of a log normal. We write it out, e to the sigma squared times e to the sigma squared minus 1 times e raised to the 2 times m power. So that's our formula for the variance of x if m was a constant. Law of total variance says, okay, well, let's figure out the expected value of that formula. So we transcribe that formula, multiply it by the PDF, and what Wolfram Alpha lets us know is there's the following formula for that expected value, with the restriction that now lambda has to be bigger than 2. So the upshot is, after everything has been simplified, derived, we have a formula for the expected value of the amount spent, and we have a formula for the variance of the amount spent as well. Square root that, we get the standard deviation. And surprisingly, even though that sounded like a lot of work, that actually saved us a bunch of time in trying to derive the marginal distribution of the amount spent itself. We have that shortcut, and so we could use it here to very quickly summarize what the average and standard deviation was of x just all by itself, freeing itself from the dependence on that random parameter describing its conditional distribution. So I think in this class, the discussion of hierarchical models really illustrates that we need to choose to be good at one of two things. We need to either be really good at math, as we've seen here, to actually work through all of the computations with hierarchical models, or we can be really good at computer programming. And I think that being good at programming, and specifically Monte Carlo simulation, really pays off, especially in the context of hierarchical models, because it is extraordinarily easy to write a Monte Carlo simulation that generates random numbers from within this hierarchy, and then we can study any property of the distribution, getting the average, the standard deviation, the probability of getting an x bigger than 40 with very little effort. So for our spending example, let's say that the distribution of the amount spent given m is well described by a log normal distribution with that parameter m and that parameter sigma equal to 1. And let's take that the distribution of that m parameter is exponential with a rate, a lambda equal to 10. How could I just very quickly generate random numbers from this hierarchical model to get random numbers for the amount spent? Well, very easy. What I could do is to just write a for loop to go through one by one. The first thing that I'd want to do is generate one random number from that exponential distribution. So REXP 1, 10, one random number, the rate of 10. And then go ahead and generate a number from that log normal random variable with RL norm. Do one of them with parameter m and 1, the number that I just generated, comma 1 for that standard deviation parameter, that sigma parameter of the log normal. If I go and do this, the simulation is over in just a second. If I ask for the average, if I ask for the variance, I find that the average from my simulation, the variance from my simulation, match up exactly to what my formula suggested they should be. It's a lot easier than going through all that math, asking Wolfram Alpha to do all those integrations. You know, hopefully you didn't make a typo. We'll put it that way.